Welcome to today's paper reading. Today's paper is titled CLLMs, Consistency Large Language Models. This paper was published in the Proceedings of the 41st International Conference on Machine Learning by Siqi Co. and colleagues from Shanghai Jiaotong University and University of California, San Diego. The abstract introduces a novel approach to improving the efficiency of large language model (LLM) inference through parallel decoding methods like Jacobi decoding. While these methods show promise by transforming the sequential decoding process into parallelizable computation, they currently achieve minimal speedup compared to traditional autoregressive decoding. This is largely due to the inability of Jacobi decoding to accurately predict more than one token per fixed point iteration step. To tackle this issue, the authors develop a new method aimed at achieving rapid convergence to the fixed point on a Jacobi trajectory. This is achieved by refining the LLM to consistently predict the fixed point from any input state. Extensive experiments validate the effectiveness of this approach, demonstrating significant speed improvements of 2.4 times to 3.4 times while maintaining generation quality across various benchmarks. The code for this method is publicly available on GitHub. Large language models, LLMs, such as GPT-4, Llama, and Palm are advancing the field of artificial intelligence. As these models are integrated into more applications, the inference latency becomes critical for user experience. Existing methods to address latency include speculative decoding, Medusa with extra guess heads, and Jacobi decoding. Our proposed consistency large language models, CLLMs, offer significant speedup without additional memory costs and minimal performance degradation. Efficient inference in large language models, LLMs, is a critical area of research, broadly categorized into methods that require additional training and those that do not. The primary focus is on accelerating the autoregressive (AR) decoding process, which is often costly. Training-free methods include speculative decoding and system-oriented optimizations like paged attention and flash attention, which enhance speed through memory management and reduced hardware access. Training-required methods often involve adding auxiliary components or modifying model architecture, sometimes enhancing training-free techniques through distillation. These approaches aim to balance performance and efficiency, addressing the challenges of high inference costs in LLMs. Figure 1 illustrates an instance of a Jacobi trajectory in the context of large language model (LLM) decoding. The n-token seq represents the n-token sequence that undergoes iterative updates during Jacobi iterations. This sequence evolves from a randomly initialized state towards convergence with the n-token sequence generated by autoregressive (AR) decoding, serving as the fixed point in this iterative process. The methodology section of this paper introduces Jacobi decoding as a method to accelerate large language model (LLM) inference. Jacobi decoding reframes the LLM inference process as solving a system of nonlinear equations, which can be solved in parallel using the Jacobi fixed-point iteration method. This approach reduces the inference cost without requiring additional model components and can be further optimized by integrating the KV cache mechanism. The paper then introduces consistency large language models (CLLMs), which are adapted from pre-trained LLMs to enjoy higher speedup from Jacobi decoding. CLLMs are trained with a consistency loss that ensures they map any point on the Jacobi trajectory to the fixed point, enhancing their efficiency. The acceleration mechanisms in CLLMs include the fast-forwarding phenomenon, where multiple tokens are correctly predicted in a single forward pass, and the emergence of stationary tokens, which remain unchanged despite preceding incorrect tokens. Additionally, CLLMs acquire a linguistic concept of collocations, which allows them to predict multiple words simultaneously, further reducing iteration steps. Figure 2 illustrates the comparison of Jacobi trajectories between a target large language model (LLM) and consistency large language models (CLLMs) on the Spider dataset. Each point along the trajectory is color-coded to indicate correctness, blue for tokens that match the autoregressive (AR) results, and red for those that do not. The CLLM shows significant efficiency improvements, converging to the fixed point twice as fast as the target LLM. This enhanced efficiency is largely due to the consistency loss, which facilitates the learning of the structure of each n-token sequence given a prefix. In this section, we evaluate the performance of CLLMs across 3 domain-specific tasks: text-to-SQL, Python code generation, and graduate school math. We also test their generalizability on open-domain conversational interactions using the MT-bench. The performance metrics include the problem solve rate on GSM-8K, MT-bench score, execution accuracy on Spider, and strict accuracy on HumanEval. Additionally, we measure the inference speedup of CLLMs by comparing their wall clock speed to the baseline AR decoding speed. This includes evaluations under different decoding paradigms such as Jacobi and look-ahead decoding, as well as speculative decoding with a distilled draft model. The results show that CLLMs consistently achieve significant speedup with minimal performance loss, particularly in Jacobi decoding on datasets like Spider. Table 1 provides a detailed comparison of consistency large language models, CLLMs, with other baseline models, focusing on performance and inference speed. Key metrics include the speedup ratio, which is the ratio of the wall clock speed to the baseline autoregressive AR decoding speed. Notable results show that CLLM Llama 2-7b achieves a significant speedup of 3.0 times, outperforming other models like Medusa 2 plus Llama 2-7b with a speedup of 2.7 times and the fine-tuned Llama 2-7b with a distilled Llama 160M model achieving a speedup of 1.7 times. These results highlight the efficiency and effectiveness of CLLMs in various language generation tasks. Table 2 presents a comparison of consistency large language models, CLLMs, with various baseline models, utilizing the DeepSeek Coder 7b Instruct as the backbone. The key points highlight the significant speedup metric achieved by CLLM DeepSeek 7b, reaching 3.4 times the baseline speed. Additionally, the table notes the high token processing speed of 127.4 tokens per second for CLLM DeepSeek 7b, and its model size of 6.7 billion parameters. These metrics underscore CLLM's efficiency and performance in comparison to other models. Table 3 presents the profiling results for fast-forwarded and stationary token counts in fine-tuned models and CLLMs. The data is reported for each n-token sequence, highlighting the best-performing model and the associated n-gram size. Notably, the fast-forwarded token count includes the one token that would be correctly predicted without fast-forwarding. The counts range from 1.1 to 5.7 for fast-forwarded tokens and 0.1 to 6.8 for stationary tokens, with sequence lengths of 16 and 32 tokens. Figure 3 presents the accuracy and speedup of models trained with various n-token sequence lengths on the GSM-8K dataset. The sequence length for generation aligns with the training settings. Speedup is quantified as the ratio of wall clock generation throughput when using Jacobi decoding compared to baseline autoregressive AR decoding. The figure shows that while accuracy remains consistent across different sequence lengths, a significant degradation in inference speed is observed when the n-token sequence length exceeds 64. Table 4 compares the performance of consistency large language models, CLLMs, trained with different sizes of Jacobi trajectory datasets on the ShareGPT dataset. The trajectory dataset sizes include 20K, 100K, and 500K. The inference speedup varies with different n-token sequence lengths, such as 16, 32, 64, 128, and 256. The table shows that the speedup gradually saturates as the dataset size increases, indicating that larger datasets initially bring more significant speedup but the effect diminishes at higher sizes. Table 5 presents a comparative analysis of the performance of consistency large language models, CLLMs, against fine-tuned baseline models, specifically Llama 2-7b, on various language modeling tasks. The table highlights key metrics such as inference speed, token/s, speedup relative to the baseline, and perplexity, PPL, across different datasets including raw WikText2 and PTB. The data indicates that CLLMs achieve notable speedups while maintaining or improving perplexity scores, demonstrating their efficiency and effectiveness in language modeling tasks. Table 6 compares the performance of CLLMs trained with different loss designs on the GSM-8K dataset. The results indicate that the global consistency loss is more effective in training CLLMs compared to the local consistency loss. Additionally, increasing the ratio of autoregressive AR loss to consistency loss enhances the accuracy of the models, although it slightly compromises the speedup gains. This suggests a trade-off between accuracy and inference speed when adjusting the loss ratios in CLLM training. In this work, the authors introduced CLLMs, a new family of large language models that excel in efficient parallel decoding. These models are designed to significantly enhance the efficiency of Jacobi decoding. Unlike other existing techniques, CLLMs do not require additional architectural components or draft models, reducing complexity. Additionally, CLLMs can be seamlessly integrated with other efficient LLM inference techniques to achieve greater speedup. The authors have demonstrated the efficacy of CLLMs across specific and open domains, showing a significant improvement in generation speed while preserving quality. The work also acknowledges the theoretical possibility of misuse but suggests that the likelihood is low at the current stage. Thank you for watching.